Dear students, welcome to the lecture number 9. So today in this talk I shall prove the Urysohn metrization theorem. This theorem actually says that every regular space with a countable basis is metrizable. It says every regular space, say X, with a countable basis is metrizable. So to prove this theorem, I shall use mainly two known properties. First of all is R omega, that is countable product of R in product topology is metrizable. We have seen that proof, right? And we will use another fact that if we have any continuous function, or you can say if you have a function f, a topological space X to R omega, if you have this kind of function, then that function is continuous if and only if its component is continuous, right? We know these two facts, and then using these two properties we shall see the proof of Urysohn metrization theorem. Okay, so first of all we can write that two properties. So recall that the two property is, first of all, R omega, that is countable product of R, right? That R omega is metrizable with product topology is metrizable. So this is one property, we have seen that, right? And we have also seen that R omega with the box topology is not metrizable. Anyway, we don't need that box topology, so we need only this property, that R omega with product topology is metrizable. And the second property is, so let f X to R omega, where R omega has that product topology, so we can write that R omega has product topology Now since this f is from X to a countable product of R, so we can assume that, so this is be a function such that, say f of x equal to, say f1x up to that fn x dot dot dot, this way, right? That's when each f1 is a function from x to r, right? Now this is a function, then we prove that actually, so f is continuous if and only if each of fi from x to r is continuous, right? Now I roughly discussed the idea of the proof of this theorem. So first of all, what is my idea? So we will construct a function f from x to r omega such that f from x to fx is a homeomorphism. Okay, so if we can construct such a function, then we are done. Why? Because we know that R omega is metrizable, right? Now that implies, what is my fx? Fx is a subspace of R omega. Now being a subspace of a metrizable space, fx is also metrizable, right? Now again, what is my f? F from x to s, fx is a homeomorphism, right? That's when x and fx are homeomorphic. Now since fx is metrizable, that implies x is metrizable. Right? So we just need to construct one function f x to R omega such that that restriction function, that is, you can say it is as f as well, because you don't need to rename that because we are just restricting the codomain, right? So it is fine. So the function f from x to fx is a homeomorphism. So our focus is to construct this kind of function. Fine. Now before going to the construction of this function, we need one thing. So that is, so we need to find, so we can write it as a claim. It is, so we need to find, so there exists a countable collection of function fn, while n belongs to a natural number. Okay, so there exists a collection of function fn such that each of fn is a continuous function from x to R Okay, and with the property that so if you choose any point x and any open set U containing x, then there exists a n such that that function gives a positive value at that point and the function vanishes, that is gives the value 0 outside of the open set U. So with the property that given any point x in x and an open set U containing x, there exists n such that if n x bigger than 0 and say if n x minus u equal to 0. That's mean we have an index n such that that function gives the positive value at x and it vanishes outside of u. Fine. So we need to find such a collection of functions. Now to prove this claim, we will use the fact that x is regular and it has a countable basis. Now here proof of the claim. Now since it has a countable basis, so let the collection Bn be a countable basis for x where n belongs to natural number. Okay. Now we choose a pair. Now we choose a pair n comma m such that Bn closure subset of Bm. So this kind of pair always exists. Why? Okay, so first of all we can see that why this kind of pair exists. So here we prove the existence of such pair. Now first of all, choose any arbitrary element x from x, right? Now since Bn is a basis, that is that collection Bn is a countable basis, right? That implies there exists m natural number such that x belongs to Bm, right? Or you can choose just x belongs to some set U, open set U, then you always get a basis element, right? X belongs to Bm. So it is fine. And now what is my x? X is a point and Bm is a basis, right? Now since x is regular, so there exists another basis, or you can say another open set, right? Or we can write just open set first of all, otherwise you will get confused. There exists open set V such that x belongs to V and V subset of Bm, V closure subset of Bm, right? Now again x belongs to V. Now again there exists n natural number such that x belongs to Bn subset of V, right? Now that implies Bn closure subset of V closure subset of Bm, right? So that's mean this kind of pair is always exist. So we choose this kind of pair. So all possible pair we choose in here. So obviously how many possibilities are there? Of course it is a countable one, right? Because at most we can choose n cross n number of pairs, right? So if we choose this kind of pair, so number of such pair is also countable. That is fine. Anyway, now for this pair we can find, so for such pair so n comma m, so there exists an open set, or we can just first of all we can find there exists an continuous function say g in m such that g in m be in closure is equal to 1 and g in m x minus bm equal to 0. Or here also we can write it is a function from x to r such that this. Why this is true? Again we will use the Urysohn lemma for that. So first of all note that so a regular space with countable basis is normal, right? We proved that. So we can use Urysohn lemma. So thus we can use the Urysohn lemma. So first of all, choose a pair. So choose such a pair n comma m, that is B enclosure subset of Bm, right? Now, so let my A equal to B enclosure and say B equal to x minus Bm. Then A and B are two disjoint closed set in X, right? Now by Urysohn lemma, so since X is normal, so by Urysohn lemma, so there exists a function, or there is a continuous function we can write it is g n comma m x to 0 1. Now since it is a function from x to 0 1, we can consider it is a function from x to r as well, right? So there is a function this x to r such that g n comma m a equal to 1 and g n comma m v equal to 0. Now that implies g n comma m b enclosure equal to 1 and g n comma m x minus bm equal to singleton 0, right? Okay, now we have a collection. So take the collection of functions gmn, that is take the collection g n comma m, for which we have Bn closure subset of Bm is possible, right? And we have seen that this collection is non-empty, right? And it is also countable. Why? Because the collection g n comma m is indexed with a subset of n cross n, right? Now this implies this collection is countable. Now we claim that this collection is my required collection of functions. Why? Because first of all choose, so now let x be any point and let U be a arbitrary open set containing X, right? Now we need to find that there exists some index n comma m such that GNM, the value of GNM at X is positive and the value of GNM outside of U is 0. Okay? So why that is true? First of all, X belongs to U, right? Now since X belongs to U, so there exists M natural number such that X belongs to Bm subset of U. Why that is true? Because Bm is a basis, as that collection Bn is a basis for X, right? Okay, now X belongs to Bm. Now since X belongs to Bm and X is regular, so there exist open sets. So open set V such that X belongs to V and V closure subset of Bm, right? Again we use the property that collection Bn is a basis. Again there exist n natural number such that X belongs to Bn subset of V. Now that implies X belongs to Bn, right? That is, and Bn closure subset of Bm. And what is my Bm? That is subset of U, right? So we have such a pair Bn closure subset of Bm. Now since Bn closure subset of Bm is possible, so Gn comma m is well defined in this case, right? And what is the property of GNM? GNM has the property that Bn closure is equal to 1 and GNM X minus Bm is 0, right? Now since X belongs to Bn, right? Now that implies Gn comma m X equal to also 1, which is strictly bigger than 0, and since Bn subset of U, that implies X minus U subset of X minus Bm, right? And GNM gives the value here, it is 0. So that implies Gx n comma m X minus U equal to 0. So we are done, right? So that's mean if we have any arbitrary point X and any arbitrary open set U containing X, then we have a pair which satisfies this property, right? Now rename the countable collection Gn comma m as this collection if n, where n belongs to natural number. So This proves the claim. Now we move to the main part of this problem. So let f x to r omega be a function defined by fx equal to that f1x, f2x, this way. So where this f1, f2, f3, these are constructed as above. Okay. Now there are lots of claims, so we need to first prove that function f is 1, 1, right? We need to prove it is continuous, and then we shall prove that if we restrict the codomain, that is fx, then the function will be homeomorphism. So first of all, claim, or we can just write the proof that f is 1, 1. So why f is 1, 1? This is simple. So first of all, let x not equal to y be two function in x, 2 points in x, right? Now that implies x belongs to x minus y, right? Now since it is a regular space, so singleton set is closed. So x minus y, this is open, right? So this is open, or we can just write, right? So since x is regular, so singleton y is closed, that is x minus y is open, right? So x belongs to some set, open set U, right? Now by our required condition, that is the previous claim, so there exists a natural number n such that f of n x, right, it is bigger than 0, and f of n, that is, if this is my u, then x minus u will be singleton set 0, right? So what is my x minus u? That is the singleton y, right? So that implies fn y equal to 0, right? So we have chosen two distinct points x and y, right? And we find one function fn such that fn x is not equal to fn y. So that implies fn x not equal to fn y, right? Now that implies my function fx is not equal to fy. That implies f is 1, 1. So this part is done. Now why f is continuous? This is also simple. Now the next claim is f is continuous. So why f is continuous? Again, so each f of n is continuous and r omega has the product topology, right? Now therefore the function f x to r omega, which is defined by fx equal to that my f1x, f2x in this way is continuous. Right? Since each component of the function is continuous, so f is continuous. So we proved that f is continuous and it is 1, 1. Now let some z equal to f of x, which is subset of r omega. Okay. Now then the function f from x to z, okay, is a bijective continuous function, right? Because f is already continuous and 1, 1. Now we just restrict the codomain as the image, so it is just bijective. So it is a bijective continuous function. Now to prove that f is homeomorphism, we just need to check open set goes to open set, right? Now to check that, f is a, we can specify that f, that x to z is a homeomorphism. We only need to check that for any open set u in x, f of u is open in z, right? Okay. So suppose u is a open set in x, we need to prove that fu is open in z. So let some point z0 belongs to f of u, right? So we need to prove that fu is open. So we choose one point z0 from fu. So we need to find one open set w in z such that z0 belongs to w subset of f of u, right? So we need to find such a w. So first of all, remember that my z0 belongs to fu. Now since z0 belongs to f of u, so there exists x0 in u such that f of x0 equal to z0, right? Now what is the property of that x0 belongs to u? So we need to use that property, right? That property of the collection of function fn. Now since x0 belongs to u, that implies there exists a natural number n such that fn x0 that is bigger than 0 and f of n x minus u, it is singleton 0. Okay, so now we use some notations to understand the fact. So first of all, what is my f? So f is a function from x to z, which is subset of r omega, right? And what is my fn? Fn is a function from x to r, right? And we know that we have pi n, which is from R omega to R, right? So we have X, R omega and R, this. So this is my pi n, this is my capital F, and this is my f of n, right? And f of n is pi n composed with f, right? Okay, so this is the situation. Now we need to find a set W. Now first of all, it is given that fn x0 bigger than 0. Now this is the idea how to find that function. That's mean if you have the point x0, right? If you take the function that is that fn, then it is a bigger than 0. So we choose the open interval 0 to infinity. So let my set V equal to pi n inverse open interval 0 to infinity, right? Now where it is a set, now does V, now then V is an open set in where, in R omega, right? But we need a open set in Z, not R omega. So what we can do, we can just take the intersection. Now let W equal to V intersection Z. Now then W is an open set in Z. Now we claim that Z0 belongs to W and W subset of f of u. Now why Z0 belongs to W? It is actually clear. Okay, so first of all we have to assume that Z0 belongs to Z. So why Z0 belongs to Z? See, what is my U? U is an open set in X, right? So U subset of X. So that implies f of U is subset of f of X, which is my Z, right? Now that implies Z0 belongs to Z. So that is clear. So Z0 belongs to Z. Now we just need to show that Z0 belongs to V, right? That's mean we need to check that pi n Z0 is bigger than 0, that is belongs to 0 infinity. Now what is my pi n Z0? Now what is my pi n Z0? Now just put the value of pi n. So what is my pi n? Pi n is, sorry, what is the value of Z0? So Z0 is f of x0, right? So this is f of x0. So that's mean it is pi n compose f x0. And what is my pi n compose f? It is fn, right? But we know that fn x0 bigger than 0, right? So it is belongs to 0 infinity. Now that implies Z0 belongs to pi n inverse 0 infinity, which is my V. So Z0 belongs to Z and Z0 belongs to V. So that implies Z0 belongs to Z intersection V, that is my W. So one part is done, right? Now we just need to prove that W subset of FU, right? Now W subset of f of u. Now again choose any arbitrary element in W. So let some Z belongs to W. Okay. Now this is subset of Z, right? Now that implies there exists X in X such that f of X equal to Z. Fine. Now also Z belongs to W means, so again Z belongs to W means Z belongs to V, right? That implies pi n Z belongs to zero infinity. So what is my pi n Z? That implies, so pi n, it is my fx, you can write, right? It is bigger than 0 just, say again 0 to infinity. So that implies pi n compose f x, it is just bigger than 0. Now that implies fn x bigger than 0, right? Now see, we have already proved that we know that fn x minus u equal to 0, right? That's mean fn vanishes outside of u, but fn x bigger than 0, that's mean x should be in u. Now since f of n vanishes outside of u and fn x is non-zero, right? That implies x belongs to u, right? Now what do you mean by x belongs to u? That implies f of x belongs to f of u. That implies z belongs to f of u. Now we assumed one arbitrary element z in W, right? Z in W, and we find that z belongs to f of u. So that implies W subset of f of u, right? So f of u is open in f of z, sorry, in just z. So thus the function f x to z is a homeomorphism, right? So that implies x is homeomorphic to z, which is subset of R omega. Now since R omega is metrizable, so z is metrizable, being a subspace of a metrizable space. Now this implies x is also metrizable. Why? As x is homeomorphic to z, right? So this completes the proof. So we stop here.